Okay, hello everyone. So the other day we talked about charge, negative, positive charge, some examples, electrons, protons, um, how to charge an object using induction or charging by friction. We talk about conductors, insulators. So let's move on. So we know there's this fundamental force in nature, that the electromagnetic or electrostatic force, and the source of that is negative and positive charges. So what's the measuring unit? We talk about this probably in the class, but let me go over this one more time. The unit of charge is called Coulomb. Coulombs, denoted by capital letter C. So for an example, let's say we have a metal sphere, and under normal conditions, let's say this is a piece of iron. This metal sphere is made out of iron, so there will be equal number of protons and electrons in it, right? So under normal conditions, it's neutral. The positive and negative charges cancels out each other's value, so the net charge is 0. But let's say we're going to remove some electrons from this, so we're taking negatives out, so electrons are coming out, so the sphere is going to be net positive. So this is how we create a charged object. We can either remove electrons from it, or let's say here's another one, a neutral sphere, and you add electrons into it. You're adding, now it's become negatively charged. If you add electrons, objects become negative. If you remove electrons, it becomes positive. You might wonder, why can't we do the same thing with protons? You can, in principle, but in reality, moving protons from an object, from matter, is really difficult, because protons are part of the nucleus. You are trying to take things out of the nucleus, which is relatively very, very difficult. And if you remove protons from something, let's say you have a piece of iron, and from those iron atoms you are taking protons out, you are actually changing the element, right? You remove protons, iron becomes something else. You add protons, it becomes something else. So the elemental changes, these are nuclear changes, nuclear reactions. Little difficult to do compared to chemical reactions. In chemical reactions, you can move around electrons fairly easy. So going back to the point, let's say you have a charged sphere or a charged object, positively charged, couple of coulombs. We can say the charge of this thing is 10 coulombs. Or another object with little less charge, we can say it has 5 millicoulombs or 3 microcoulombs. Micro stands for micro. 10 to the negative 6 coulombs, right? Microcoulomb. So as I said before, coulomb is it's a lot of charges. Let's say if you have like a 1 coulomb charge, that's a lot. Normally the charges we encounter in our day-to-day life are in micro and millicoulomb levels. And also what is the letter symbol when we talk about a couple of multiple charges. Let's say here we have a charge 1 with 1 or 2 coulombs. This is our charge 1. Here's charge number 2 with negative 5 microcoulombs. Here's charge number 3 with 10 millicoulombs. The letter symbol we use to indicate charge is Q. So we can say Q1 is 2 coulombs, Q2 is negative 5 microcoulombs, and so on. It's like distance is denoted by letter X, or the length is denoted by letter L. Same way, charge is denoted by letter Q, and the magnitude of the charge, the unit for that, is denoted by letter C, which is coulombs. Right? So we have an idea the metric unit or the standard unit for charge. Also, let's say, all right, give me a second. Also, I mentioned that by adding electrons or removing electrons, you can charge an object. So how much charge you get when you add an electron? What's the charge of an electron? Electron is the smallest charge we can find in nature, naturally existing, right? So the charge of an electron, the smallest charge, electron, and the value in coulombs is 1.6 times 10 to the negative 19 coulombs. It's a very small value. It's a negative charge. Electron has a negative charge, and this is the magnitude. There's few more decimal numbers next to it. I'll show that in the next slide. The naturally existing smallest charge is the charge of an electron, and this is the value. The positive charge, the proton, has the same number, charge of a proton. It has the same value, 1.6 10 to the negative 19 coulombs. This is positive, right? All right, so okay. All right, so what's next? So let me erase this. The next topic we're going to talk about is, now we know that charges can exert force on other charges. So for an example, if you have a positive charge and a negative charge, let's say this is charge 1, this is charge 2, there's a force between them. Opposite charges attract, so they're attracting each other with a force, and the same force, that the positive charge is feeling a force due to the negative one, the same force is acting on the negative charge. So here this charge on the force on Q1, we can say F12, force on 1 due to 2. This one we can say F21, force on 2 due to 1. Now these two forces are equal. The force on one charge due to another is equal and opposite in direction, right? So let's say you have a much bigger positive charge, a lot of positive charges, and few negative charges. There's force like this. These forces are equal in magnitude. Now if you have two charges in opposite directions, if you have two equal charges, like positive and also positive, the force will be in opposite direction. So they're pushing each other away, their repulsion. Again, this is Q1 and Q2, so this will be F12, F21, pointing in opposite directions. Now what's the magnitude? How do you calculate this force? The force depends on a couple of things. Depends on the individual charges. Like if bigger the charges, if both charges are bigger, the force gets bigger. If one is bigger, the other one is smaller, still it depends on how big these charges are. So the best way to explain that is, it depends on the product of the two charges. So if one is bigger, the force gets bigger. So the force depends on Q1, Q2. So we're going to talk about the force between two, and then later we can add more more charges into this, right? But let's look at the simplest case. If you have two charges in front of each other, what's the force between them? It depends on the product of the two charges. It also depends on the distance between them, but in an inverse manner. Let's say here you have Q1, this is Q1, Q2. So when we draw them like this, we call them point charges. And in most of our calculations, we will denote a charge using a little dot. We call it a point charge. So that way we don't have to worry about its dimensions, how the width or the length of this charge, the shape of it. We take it as a small spherical dot without any dimensions, right? So let's say the two charges are at some distance. So there is some force between them. If I increase the distance between them, the charge magnitude same, it's still Q1, Q2, but now the distance is much bigger, force gets smaller. Right? This is a big force, a small force. If I bring them closer, Q1 and Q2, force gets bigger. So the force depends on the distance or the separation between them, but inversely. It's an inverse relationship. Means if one increases, the other one decreases, right? So F depends on distance or the separation, or we say center to center distance. Like if you have two spheres like this, we have to take, like in this diagram right here, we have to take the center to center distance. Depends on distance inversely. I don't remember how to write it. So 1 over distance, right? That's the inverse relationship. Okay, so let's put this into an equation. Let's go to the next slide. This is called Coulomb's law. Experiment shows that the electric force between two charges is proportional to the product, directly proportional to the product, and inversely proportional to the distance between them. So for mathematical purposes, we mark the two charges Q1 and Q2. You can use capital Q, that's fine. And the distance between them, we label it as R. This doesn't mean a radius, it's the distance between the 2 points. And then the Coulomb equation is given like this. Let's go to the next slide. Coulomb's law says the force between the two charges is K times Q1 Q2 over R squared. That's the force. This is Coulomb's law. This equation gives the magnitude of the force between the two charges. Okay. All right, let's talk about the details of this in a second. So here you see the equation on the left. Coulomb's law says the force is K times, it's a constant here, we call it the Coulomb's constant, K times Q1 Q2 over R squared. Now what is the magnitude of this term K? This thing here, the Coulomb's constant, K is given as 8.99 times 10 to the 9 newtons meter squared per coulomb squared. So this is a universal constant. It's called the proportionality constant. For our calculations, we can even take it as 9 times 10 to the 9. That's pretty close, and it's a good approximation. So this equation tells you how to find the force between two charges. So let's try one or two examples. Okay, clear this. All right, so let's talk about this epsilon symbol in a little bit. So let's see whether we have any examples. Which charge exerts a greater force? So we have, let's try this example. Two positive point charges, Q1 is 50 microcoulombs, Q2 is 1 microcoulomb. So here's Q1 50 on the left, Q2 on the right, separated by a distance L. Which is greater in magnitude, the force that exert? Okay, so L is not given. Let's say L is what? 2 meters. Alright, so here we have two charges, Q1 and Q2, separated by a distance of 2 meters. Now the question is asking, now we have two positive charges, right? Positive point charges. So we know the force will be pointing outwards between them. And we call this F12, F21. We already know that, we talk about it, that the two forces gonna be the same in magnitude. Now we can either do some math and show that. You can always plug this to the equation and see what the answer is. So let's try that. Let's find the force in general. Force equals K times Q1 Q2 over distance squared. So the value of K is 9 times 10 to the 9. Charge 1, 50 microcoulombs, 10 to the negative 6. Charge 2, 1 microcoulomb, so that's 10 to the negative 6. This 10 to the negative 6 is for micro. Divide by distance square, so 2 square. Now you take the calculator, plug in the numbers, do the math, see what it is. Okay, let's see. Hoping that I did this right. Looks like you guys can always do the math and check whether you get the same answer. Now, regardless, if you calculate F12 or F21, you will be plugging the same numbers to this equation, right? The two charges will be 50 times 1 or 1 times 50. It doesn't change. The numbers remain the same. The distance 2 squared, K value remains the same. So F12, F21, you get the same answer. The only thing is they are in opposite directions. F12 is pointing to the left, F21 is pointing to the right. So the force is going to be equal, and this is how you do the math and find the force. Okay? Alright, let's see what else we have. Oops. Let me fix that real quick. Let me clear this. Alright, so there's few more examples like this. We'll get to that probably in class. This I will explain. Actually, let's talk about, let's see. Yeah, so this K value, alright, hold on. Okay, so the equation says force equals K times Q1 Q2 over distance squared, and we know that K is 9 times 10 to the 9. Now K is not a fundamental number. K is more like a composite number. There's a couple of things inside it. Later we will learn, when we come to electric fields, we will replace this K with another constant, same thing, but we write it this way, 1 over 4 pi epsilon naught. This is still the same magnitude. But if you want to know what this epsilon naught, or the permittivity of free space, we take this to the other side. Epsilon naught is 1 over 4 pi k, and you plug the numbers. 1 over 4 pi, you know what pi stands for, it's 3.14 multiplied by 9 times 10 to the 9. It gives you the magnitude of epsilon to be 8.85 times 10 to the negative 12. Okay, so we will talk about this later, not right away. So this permittivity, also a very important constant. Permittivity tells you, it's the idea is like how much electric field or electric force is allowed to go from one charge to the other. So this equation, force between two charges, F equals K Q1 Q2 over R squared. So you have two charges, Q1 and Q2. Let's say they are opposite charges, so the force is pointing towards each other. These are not contact forces. Contact means they are not in contact with each other, right? The two objects are separated. So we call these forces at a distance. So something needs to go from one to the other. This is a difficult question early scientists battled with. If two objects are not in touch with each other. Remember in a previous semester we are pushing boxes across the floor, we calculate friction, acceleration and all that. So you're pushing, this means you actually physically have to apply the force. It's a contact force. Now these things don't have that contact, right? The objects are apart, there's separated, there's distance between them. So how do each other feel these forces from the other side? So they came up with the idea of electric field, a method of transferring force from one place to the other. We'll come to that later. But this permittivity constant is important when you talk about electric field. The medium between the two charges. Now right now we can say it's air is in between them, right? Atmosphere. How much this atmosphere is letting this force to go to the other side. That's the idea, kind of the idea of the permittivity. Anyways, that's not important right now because the slide is here. I wanted to talk about it. What you need to know for the next set of questions is, if you have two charges and to find the force between them, we use the above equation, this equation right here, and the K value, the two charges, the distance between them square, gives you the force in newtons. Force comes in newtons. Q should be in coulombs. This should be in meters. The force will be in newtons. Okay? Alright. The next thing, if they're opposite towards them, if they're equal, like two negative charges away from each other. And I want you to think about different possibilities. What if I put three charges in the same line? Let's say positive, negative, and positive. And I ask you to find the force on the one in the middle. So there'll be a force on this negative guy pointing this way. So if this is Q1, Q2, Q3, we can say this is F21 going this way, and there'll be a force on this side which is F23. The net force on Q2, what do you think? I want you to figure this out. What if I place them like this, one here, and one here? Let's say positive, negative, or positive, positive, positive. What's the force on Q2? So repulsion, there are going to be a repulsion pointing this way, there are going to be a repulsion pointing this way. What's the net force? So these are the kind of questions we're going to discuss. All right. Okay. I think that's enough with Coulomb's law, Coulomb's force. So we'll talk about some problems soon. All right. Thank you, everyone.